Hi everyone, welcome. Today we are going to go over Nanoacademic live on qBraid. We're going to let a few more people filter in and get started at 12 in the next minute. While you wait, you can go ahead and take a look at this slide. There's a few tidbits of information and a short agenda on there. One thing I will call out is that everybody attending live does get 50% off qBraid credits, and we'll show a short demo how you would do that momentarily here. All right, great. I think we're ready to get started. So as more people trickle in, they can follow along with us. But yeah, welcome everybody. Thank you so much for joining. Good morning to everyone, or evening, depending on your time zone. My name's Alex from qBraid, and this is session 2 of the qBraid community webinar series. For anyone joining the first time, qBraid is a cloud platform that provides access to over 20 QPUs and browser-based lab IDE where you can develop, deploy, and run quantum programs locally or in the cloud. So a little context about our series today. This series is a 4-session series with the idea to be bringing on the companies building the tools and hardware behind quantum and scientific computing, and they'll show you their work running live inside qBraid. So we'll be doing real demos today that you yourself can run afterwards. Session 1 was with NVIDIA on CUDA-Q, and that recording is now up live on our YouTube if you happen to miss it. Today we'll be focusing on Nanoacademic. Before we start, we're going to do some quick housekeeping. First, please put your questions in the Q&A tab at the bottom of your screen. You'll click the button there. It will say more, and then just click on Q&A and not the chat. We won't be using the chat today. So any questions, just go through Q&A tab, and we'll answer the quick ones in writing as we go. We'll have some breaks during the presentation where we can get to those. And then we'll have 10 minutes at the end to answer any bigger questions that people may have and open up the floor to more Q&A. Second, we are recording this demo, so you'll get the recording by email afterwards, along with a few resources and a follow-up. If you happen to miss that email, all you need to do is go to qBraid YouTube channel. Just look up qBraid on YouTube, and you'll be able to find this recording posted there. There are a couple of polls this session, so please just keep an eye out for those, and we'll answer a few questions there. So to start, we'll do some quick getting started on qBraid, just to show you how to first redeem your credits that you'll get from this session if you are planning to purchase. Or if you want to just try our free features, go ahead and get started on those. So after that, I'll hand it over to Nate and we'll close with Q&A, as I said. Great. So I'm going to switch over now to a very short demo of qBraid for anybody getting started. All right, give me 1 second here. All right, so when you first start out, you're going to land on this dashboard page. What you want to do is go to account.qbraid.com. Once you're there, you'll see a sign in or sign up page. For those of you new, you're going to go ahead and sign up. Just fill in the information details there and do the email verification. Once that's done, you'll have a quick questionnaire and a short tutorial. Feel free to skip that tutorial for now, as I'll show you most of the features. You can always come back to it in the top right corner. If you click this question mark, there'll be a tour menu here, and it'll go over some of the key features of the platform, such as submitting jobs. Everything on qBraid runs on credits, so you'll be able to see your credits here in the top left. If you're new again, that will be 0, but if you're interested today, what you can do is actually go to this wallet page on account. If you can't quite see it, just make sure you scroll down on the sidebar, click on the wallet tab under the account section, and you're going to scroll down to buy credits, or you can click this add credits button here and scroll you down there automatically. So you're going to use that qBraid community promo code and just type it in there that I just showed, and I'll type that in the chat here as well. And just click purchase. You'll go through Stripe purchase, and then you'll have credits. Obviously, you can use our free plan, so don't feel like you need to go do that right now as we're getting started, which is plenty of features included. So I'll run over a few quick things here. We have qBraid Lab. This is where you'll launch your IDE on any instance. So small instance, medium instance, large instance, we have plenty of CPU sizes to use. We also have quite a few GPUs if you want to run bigger data. Here, you can go ahead and use some of the latest GPUs. This will cost you credits, as I said, on the on-demand instances, but all of these CPUs you have access to for free. So you can go ahead and launch those if you're curious, and you'll see a launch startup loading bar. And then once that, it will redirect you to a new tab. One other thing I'll point out is our AI tool right here, which we will be talking about Nanoacademic's AI tools as well. And here you could submit a job. So if you're curious about submitting your first job, I would just recommend you to type in something like, please submit me a Bell circuit to qBraid's QIR simulator, which is a free simulator. And it'll walk you through the steps there. It'll ask you a few questions, and you'll be able to submit a job just through your agent. So just, follow along there, and you'll be able to submit your first job, which will show up in this jobs tab here. You can see I have 399. If you go over to this all jobs, you'll be able to see that. Again, this is all in our tutorials in the top, so don't hesitate to go through that yourself. Great. So that's a quick demo there. And again, I'll send that. Now I'm going to do a quick intro to Nanoacademic. So Nathaniel Vegh is joining us from Nanoacademic, who build first principles simulation tools for materials, nanoelectronics, and quantum device research. Their stack is RESCU for large-scale DFT, NanoDCAL for quantum transport, and LatticeMind, an AI agent that takes a calculation you describe in plain language and builds it. So the last point is what we'll be focusing on today across, as well as all of the other tools in that stack, and Nate's going to run it live. So I'll hand it over to Nate, and he can give a brief introduction. We can get started with our demo. Thank you.
Awesome. Thank you so much, Alex, for the kind introduction. It's a real pleasure to be here with the qBraid community. I'm just going to start sharing my screen. Please let me know if you see it showing. Is it all good?
Still see it presenter mode, Nate, if you want to switch it over.
Let me see. Share. Oh, it's no presenter mode.
Yep, looks good.
Does it look good now?
Yep, yeah, we can see it.
Perfect. Awesome. No props, technology. So, hi everybody, my name is Nathaniel Vegh. I'm an AI and computational physics researcher at McGill University and the lead developer of LatticeMind at Nanoacademic Technologies. So today I'd like to show you how we're using AI to make first principles simulation workflows much easier to build and run with LatticeMind, and we're going to do a few live demos together on qBraid. So before we get there, let me give you more of an introduction of Nanoacademic and the tools behind the calculations you'll see today. So Nanoacademic is based in Montreal, absolutely beautiful city. It's close to Chicago too, so come visit. And our mission is to build atomistic and quantum modeling tools for next generation materials and quantum devices. Our tools have supported several hundred peer-reviewed studies. Today, that work rests on three complementary product families. NanoDCAL is our first principles quantum transport simulator, combining DFT with non-equilibrium Green's function to predict charge and spin transport through nanoscale devices directly from their atomistic structure. RESCU is our density functional theory, or DFT solver, It's designed for first principles materials calculations, and it excels at very large systems. And QTCAD works at the device level. It uses finite element methods to model quantum hardware, including the electrostatics and qubit physics of real devices. These tools have supported real hardware. The machine on the right is a 6-qubit quantum computer from Equal1, whose qubits were simulated using Nanoacademic software. The latest addition is LatticeMind, which we'll spend a lot of time talking about today. LatticeMind currently supports RESCU and NanoDCAL. In the live demos, you'll mainly see us working with RESCU, and in the recorded demo, you'll see NanoDCAL as well. So before we get into LatticeMind itself, I want to spend just a few minutes showing you what these simulation engines can actually do, and you will have access to them on qBraid. So let's start with RESCU. One of the main strengths is its scale and range of first principles calculations it can handle. So on the left here, you can see it's a graphene on a hexagonal boron nitride Mori superlattice. That's over 12,000 atoms in a single supercell, and we can treat that fully from first principles. RESCU also supports density functional perturbation theory, or DFPT, for calculations such as phonons or Raman spectra. Here, the calculated Raman peaks are compared directly with experiment. And this is an example from my own work recently in silicon and germanium spin qubit materials. We use RESCU to simulate the band offsets at silicon SiGe and germanium SiGe interfaces, which determine quantities like the depth of the quantum well and the height of barriers that confine the carriers. So that gives you a sense of the range from very large material calculations to spectroscopy to material calculations that feed directly into quantum device design. That's on the materials side. NanoDCAL takes us to nanoscale device physics with quantum transport. The first example is from work that my colleagues published earlier this year. At the top, you can see a clean aluminum oxide Josephson junction, and then the same junction with a single hydrogen atom added at the interface, circled in blue. Underneath each structure is the self-consistent potential calculated by NanoDCAL. And what's interesting is that even a single atom of hydrogen could change the potential landscape, and then the qubit physics. From there, NanoDCAL can also calculate transport characteristics directly from first principles. Here, for example, is a current voltage response for a transistor, and it extends to spin and light-driven transport as well. This example shows a spin-resolved photocurrent in a two-dimensional device. So between RESCU and NanoDCAL, we can go from electronic structure of a material all the way to nano-scale device behavior. And that brings us to the main problem we're trying to solve. These solvers are very powerful. But getting from a scientific question to a result you can actually trust involves much more than simply running the code. You first need the right structure, the right coordinates, and also the right units, which we can sometimes forget. Then you need the numerical inputs, pseudopotentials, K-point grids, resolutions, functionals. Once the calculation runs, you still have to configure and check that everything converges. And in a multi-stage workflow, every calculation has to use the correct output from the stage before it. There's lots of dependencies. And the handoff is especially important because a wrong file or path can quietly affect everything that follows. And then there's analysis and post-processing. Finally, you get a number. And if it doesn't agree with what you expected, you have to ask, is it the physics or did something go wrong earlier in the workflow? And that's the key point. A DFT result is only as reliable as the workflow that produces it. And a lot of that workflow is still assembled manually and checked manually. Before I show you what we did about that with AI and with LatticeMind, I have two quick questions for you. First question, have you used an AI assistant or AI agent to automate part of your scientific workflow before? Please answer yes or no. I'm very curious. Thank you, Alex. So we'll give everybody about 30 seconds. And of course, we're using AI a lot these days for coding and for web development, for all kinds of stuff, even for PowerPoints. But can you trust it enough to handle scientific workflows for you, or have you tried using it?
All right. We'll end
All
the
right.
polling.
Oh, yeah, we have a split here. That's very interesting. So we have 42 out of 74 that picked yes, so that's 57%, and 32 out of 74 that said no, 43%. So that's very interesting. So for those of you who said yes, we're going to introduce a new tool, and you can play around with it. For those of you who said no, So this is something new, and we're very excited to show you. Awesome. Second question. In your own computational research, so what would you most want help from an AI agent? Maybe it's building the structures and geometries, literature research, managing multi-stage workflows, post-processing, or choosing parameters and checking convergence. This is a multiple choice question, so feel free to select everything. I imagine a lot of people started using AI tools like LLMs or ChatGPT on the web with literature research. But with the rise of AI agents, a lot of the other items are, starting with post-processing, and some of the other items are becoming available as well. All right, let's take a look at the result. Oh yeah. A lot of people chose post-processing and literature research. So those are like the two most popular choices. Uh, and spoilers alert, basically LatticeMind will support all the features listed here. And we're going to show you that live on the qBraid platform. Awesome. So what if you just give the modern models the documentation? Will you be able to trust them? And nowadays we know that they can produce individual solver inputs that look very reasonable. They can write very good code. It's natural to assume they can write pretty good input files. But the harder problem is when you ask them to build a complex multi-stage project, which is much closer to real scientific work. So here we gave 3 models the full RESCU documentation and asked them each for a 2-stage workflow. First, we asked GPT to do a relaxation for silicon and then band structure. But instead of using the relaxed geometry produced by the previous stage, it fed the perfect structure again into the band structure calculation. So it doesn't use our relaxed geometry. We asked Gemini to first do SCF with PBE and then feed the converged density into an HSE calculation. But one of the requirements of doing HSE calculations in RESCU is that we need to use gamma-centered K-point grids. However, you can see we're using even numbers over here. And we gave Claude the same prompt this time to do an odd-centered K-grid. But then there's another requirement in RESCU where when you're using an LCAO basis, you have to use an all-odd K-grid. So the important point is each of those files actually look quite reasonable on their own, but these tiny details matter a lot in scientific calculations. And you can see how those errors can accumulate and compound over large multi-stage complex workflows. So here's another example. This is a silicon SCF input generated with full documentation. So this actually looks excellent. All the keywords are real, and the structure looks reasonable, and the workflows are connected properly. So this would actually run in RESCU perfectly with no warnings. Would you run it? There's one problem. 10.25 is the silicon's lattice constant in Bohr, but the file declares it in angstrom. So that's the structure it actually builds compared to the real silicon lattice. And that's where the error is kind of dangerous. Nothing crashes. Everything looks clean. But in scientific research, that's not enough. Generating plausible inputs is not enough. So we need some way of checking the science before the inputs are allowed to run. Those runs can be very expensive. In our 44 case benchmark, direct LLM workflows with documentation produce valid workflows 1% of the time. With our validation gate and agentic harness, all workflows in our benchmark, 44 cases, over 3 rounds, were accurate and physically consistent. And that brings us to LatticeMind. So this is LatticeMind. The idea is fairly simple. You describe the calculation you want in plain language, and LatticeMind turns that into a complete simulation workflow. It plans the calculation, builds the structure, generates and validates the inputs, runs the solver, and produces a report. It currently provides mature support for RESCU with NanoDCAL and VAST support and preview. It can run locally on HPC or even better on qBraid. So you can choose the language models behind it, including self-hosted models. Here's what makes it different. The common approach for agentic systems is on the top, where you generate something, run it, see what breaks, and then repair it afterwards. That makes sense when execution is cheap, like in web development. But scientific calculations can be very expensive, and that's what we just saw. So LatticeMind works the other way around. So before execution, it defines what each stage needs, what it produces, how the stages depend on each other, and then it checks the generated inputs against that workflow. And then we would have adversarial agents validate the scientific accuracy in claims. If something fails, it repairs it and checks again. Only after all that, we'll send the input file to the solver. So the basic principle is very simple. Nothing reaches the solver until the workflow passes validation. Here's what it looks like in practice. On the left, the user asks for a spin polarized calculation for BCC iron. LatticeMind turns that into a two-stage workflow, first SCF, and then density of states. The contract makes the dependency explicit, so the inputs generated are validated, the workflow runs, and then we get the scientific results on the right. So the loop is request, plan, validate, execute, and report. Of course, the next question is whether this works consistently. So we built a benchmark of 44 workflow tasks. Across each of the 3 language model backends, all 44 out of 44 pass the reference checks. And across 132 total runs, 119 passed on the first validated plan. The remaining 13 needed 1 repair, and all those repairs happened before it reaches the solver. On the VAP subset, we did 19 small benchmarks, and we saw 19 out of 19. So we can see the same validation workflow works with different models and different solvers. So how much of this is simply about choosing a better language model? We tested that directly. With the full validation gate, we get 100%. With trial and repair, where the problem is only discovered after execution, 71%. And with direct language model generation, even with the documentation available, about 1%. And the failures on the right are exactly the kinds we've already seen. So incomplete workflows, malformed structures, hallucinated keywords. So the takeaway for us is the reliability doesn't just come from a bigger model. It also comes from the system around the model. And that matters a lot for a few practical reasons. First is privacy. If you're working with proprietary structures or results, you don't want the data to leave your environment. And because LatticeMind isn't tied to a particular model provider, you can use a self-hosted language model and keep the entire workflow local. Second is cost. You'll notice that all of the examples I've shown you, we're using efficient or like speed tier AI models. Smaller and self-hosted models can be dramatically cheaper. We're talking about hundreds of times. And the validation layer allows us to use them much more reliably. And third is education. On qBraid, students can work directly from a browser without spending the first part of the course, installing, configuring scientific software. And with LatticeMind, they can get started with calculations very quickly without worrying about the nitty-gritty details, which they can look up later. So the same architecture gives us 3 useful directions: private, affordable, and teachable DFT. Since this is the qBraid community, we pointed LatticeMind at a device I suspect that a lot of you will care about, a Josephson junction. Since this calculation takes a while, I prepared a 5-minute video to show you what LatticeMind can do. So I'll stop sharing my screen here. And oops, computer's frozen a little bit. All right. Please let me know if the audio and the video looks good. Welcome to LatticeMind, a validation-gated AI assistant for density functional theory workflows. First principle simulations are powerful. Turning a scientific question into a trustworthy result requires many connected steps. You need to prepare the structure, choose the physical parameters, generate solver inputs, and analyze the results. LatticeMind turns a single plain language prompt into a complete and executable DFT workflow. You can work with LatticeMind through 2 interfaces. The visual web interface lets us create, spec, and manage the project. For scripting and automation, we can use the command line interface. All interfaces work with the same project folder, so we can move between them without losing our progress. Let us begin with a familiar example, the electronic band structure of silicon using the PVE function. From this request, LatticeMind builds the 2-atom silicon cell and creates a linked 2-stage workflow. First, it prepares a self-consistent field calculation to obtain the ground state electron density. It then prepares a band structure calculation that will reuse the converged density. Before launching the solver,
LatticeMind validates the generated project. It checks the structure, calculation setting, required files, solver keywords, and the dependency between the two stages. This validation gate is important. An input file may look correct while still being incomplete, physically inconsistent, or connected to the wrong upstream result. If a check failed, LatticeMind can repair the project and validate it again before execution. After we click the Approve buttons, the calculation will start running. LatticeMind records its status and monitors the files produced by the solver. Once the converged density is available, the dependent band structure calculation can begin. This ensures that the workflow runs in the correct physical order. The completed calculation gives a PBE band gap of about 0.586 electron volts. You can see the band structure here. Alongside the final report, LatticeMind preserves the input decks, raw solver outputs, execution records, and generated figures. The project can now be inspected, modified, rerun, or extended into a more advanced calculation. Next, we ask LatticeMind to calculate the spin result band structure and density of states of ferromagnetic BCC iron. LatticeMind creates the BCC iron structure and initializes it in a ferromagnetic configuration. It then constructs a three-stage workflow consisting of a self-consistent field calculation, followed by band structure, and then density of states. I reuse it to converge the electron density. After the calculation completes, you can see the generated plots in our final report. LatticeMind also supports NanoDCAL for electronic structure and quantum transport workflows. This is a 261 atom aluminum oxide, aluminum junction paired for NanoDCAL. The system contains 2 electrodes and a central scattering region. These components must be calculated in the correct order. The device calculation depends on results produced by the electrode and central region stages. It prepares the required NanoDCAL input decks, basis files, post-processing scripts, and execution settings. The calculation has now completed successfully. The final report brings together the junction geometry, workflow status, transmission results, solver files, and extracted quantities. For this demonstration, we used coarser computational resources to reduce the calculation time. For production quality calculation, LatticeMind would be used to perform the appropriate convergence tests and determine suitably refined parameters. LatticeMind is a practical AI assistant for density functional theory and quantum transport. It turns a one-line scientific question into a structured project with validated inputs, explicit dependencies, managed execution, interpretable results, and documented scientific limitations. From scientific question to reproducible evidence, this is LatticeMind.
Awesome. So now let's see some action on the qBraid platform. So first, I would like to, okay, no problem. I would just like to walk through the installation process and how you can get started with LatticeMind on the qBraid platform. There are 2 methods. So first, you can do it through the subscription instances here, or you can do it through on demand. So I'm going to walk through the subscription method first. And we have a full guide included here in the qBraid exploration page. So if you go to Explore, you'll see Nanoacademic over here. And then if you scroll down, you'll see the Getting Started Quick Start section. It provides a step-by-step tutorial to help you get everything set up. First of all, you'll need a Nanoacademic account. So you need to go to Academic. And sign up and go to the client portal and to get your license. My colleague, Jeremy, is also here. So if you have any questions regarding Nanoacademic licenses, feel free to add it in the Q&A. So we have a small instance ready over here. That's the first step. And then you would need to open the environments panel over here. You can see I already have everything installed. I won't be installing the whole thing. The process takes some time. So I'll show you very quickly all the necessary steps that you have to go through. You would go to environments, search for Nanoacademic, and then you would see this. Go to the latest instance, and then you would want to install it. After you install it, you'll see this new Python 3 Nanoacademic Python shell. And then you would want to print your environment. So you would run these commands. And then this would give you the path to your Nanoacademic environment. What you want to do is list this directory, and you'll find the activate script over here. So you would need to do source, activate, and now you're in the Nanoacademic environment. And then you can start exploring and using all the different Nanoacademic products. To configure everything, of course, you would need a Nanoacademic license. So you would log in here using the same credentials you have on the Nanoacademic website. For LatticeMind, you would set up an OpenAI API key. And to actually use all the software, you would need to download these licenses. It's very easy to use. Everything is configured here. And one more thing you would need to do is to install the MATLAB runtime over here. This process takes a few minutes. I have everything set up already, but I'm going to switch to my other instance over here. I might need to refresh and start it again. For the purposes of this demonstration, I'm going to use this instance. It will only take a few minutes to start. So what I'm using is an on-demand instance here, the Nanoacademic small instance, which has 32 cores, 32 CPU. It will take a few minutes, and I will run one command to install the latest version of LatticeMind. That's basically all you need to do. And then we'll run some live examples together. I have quite a few prompts prepared for today, so let's see how many of them we can go through. I will demonstrate both the CLI and the web dashboard. So meanwhile, let me, since we're doing the live demo, let me take a look at the webinar chat, the Q&A. More Q&A. Awesome. You could have used Gemini Pro. Where can I find physics and mathematics part? Can you have access to? Oh, so Alex, will the participants have access to the slides afterwards? I can send it to you, of course.
Yeah, definitely. If you're good to send it over, I can send that out in the follow-up email with the additional
Perfect.
resources.
Let's see. And awesome. So I'm going to install the latest version of LatticeMind. So for one of the questions, it was someone was asking, you could have used like Gemini Pro. So that would be a more frontier model. And so one of the things that we did in our studies, so we have a manuscript, we have a preprint, and I will attach a link to it at the end of the presentation. So even with frontier models, they are prone to make the same kind of mistakes, just at a much lower rate. But the problem is when you have larger projects, those, even if it's at 90, like let's say 99% accuracy, if you have 13 workflow steps, then the probability that your entire project will still be valid drops down to like 50% because it's a compounding problem. And another problem with frontier models is that the costs can be very high. It takes a lot of tokens to feed the full context of complex scientific software. So using frontier models, especially for large-scale calculations, could be very costly. And it also makes it impossible for you to use a smaller self-hosted model for calculations that might be a bit more sensitive.
So I have CD'd into a LatticeMind outputs directory and launched LatticeMind. So that's all you need to type. This is for the CLI. I'm going to do an example in the CLI first, and then we can do one in the web dashboard. So the first example we'll try is an SCF band structure for silicon. It's a nice example because it's always very quick. It's multi-stage, and everybody loves silicon. Let's see if I have any more Q&A questions. Where can you find the physics and mathematics parts required for it? Could you elaborate? So if you meant the physics and mathematical parts of like RESCU and NanoDCAL, you can go to the Nanoacademic documentations page. We have lots of theory and guides for you to go through. That's where you can find the mathematics and physics part of it. Yep. So LatticeMind has started. You can see it generated the directory structure for your project. There is a new project being created here. So we have an SCF file, band structure file, all the result directories, and the scripts for post-processing. How certain this would go from real research to prototype production? Yeah, so what we are developing here is geared towards production scale calculation. So it's not just like a prototype demo. You can start using LatticeMind today, even for some of your challenging calculations. And we are actively developing comprehensive benchmarks to test and expand LatticeMind's capabilities. So many of the existing agentic frameworks are still testing more basic calculations, like maybe two-step calculation. Many of the existing benchmarks are two-stage workflows, but with LatticeMind, we're trying to really make it even nested and complex, real-world multi-stage workflows for scientific calculations. So you can see LatticeMind has launched RESCU. So if you didn't see what I typed over there, LatticeMind generated these input files. I can show you over here. Input files for silicon and for the band structure. And then it asked me for the permission to launch RESCU on the cube already installed on the qBraid machine. And this is RESCU running live. And thanks to qBraid, it's super quick. We're going to do post-processing right now to plot the band structure. Yeah, so would like to answer. Oh, yeah. Yeah, so at Nanoacademic, because we have so many years of experience in first principles calculations, we've also accumulated a lot of expertise, a lot of in-house data, and that's what allows us to make sure that LatticeMind is reliable for scientists actually doing first principles research. So the full report is ready now. At the end of a LatticeMind run, what you get is this, a report. It's a polished report, which you can go through. It shows you everything that has executed, the directory structure, all the input files generated, and the step-by-step procedure. So this would be very valuable for new users or students. And it shows you the results at the end. So we can continue this request. So we have a band structure plot now. So I want a DOS plot on the same project, and we can just do that. So just continue with the DOS calculation and plot. LatticeMind will detect all the things that are already run and completed, and won't waste any work rerunning any of the calculations for you. Just go to the Q&A again. Awesome.
So you can see run rescue now for one of the three inputs to have already completed. We're going to say yes. And of course, all of this is skippable. In your settings, you can say just auto run, and then you can just start the prompt and then go grab coffee, and then you wouldn't need to be here and type yes. So right now you're seeing rescue, but we are actively developing new benchmarks for NanoDCAL and VASP to make sure that we can do very reliable calculations on those as well. So in our benchmarks, it's not just validating, oh, the full workflow is done and a return and exit code of 0. We actually validate the physics. So we grab a lot of the values, say, from literature, materials project, and we compare the final produced results with them. So it's not just about building the software infrastructure for orchestrating your workflows, but it's also integrating the scientific part of it, the scientific reasoning into it as well. And that's why you will see that we also have a researcher note in our video. So we're just finalizing with the post-processing. So for those of you who prefer a more visual and more interactive experience, I'm going to demonstrate the web dashboard next instead of the CLI. All right, so we have the report. And let's go to end. This one's probably not, oops. Probably not completed yet. Search. Okay, so we have the new report here. So we have a new DOS down here. Awesome. So I'll move on to our web dashboard, and we're going to try with a different structure this time. To launch the web dashboard, there are two ways. You can either stay in that previous CLI and just type in /web. So I'm going to do web, or you can do LatticeMind-web. To actually use the web dashboard on qBraid, you would need to copy this, replace the lab part with proxy, and then type in the port number with a slash. So we're going to do gallium arsenide this time. We're going to start a new project and do gallium and arsenide. So I realize we are running short on time, so hopefully this wraps up soon, and I'll do one more SCF convergence for aluminum. Yeah. We'll do a convergence study for the K-point grids. In the web dashboard, everything looks a little bit more intuitive. You can see all the different nodes working together, the event logs. And if you're interested, you can even take a look at the insights and what the things the AIs are thinking about. Can I calculate for new materials that haven't been explored yet? So yeah, I guess for DFT, that's what we do, right? You can definitely ask it to try to assemble new structures together. It will put together a structure builder, build it for you, and then run it in rescue. Here's to understand how you handle users who are not experts in DFT. So that's a very good point. So that's what LatticeMind is for. For people who are very new to DFT, they probably don't know how to configure all the parameters. As you saw in the input files, they can get very sophisticated very quickly. But with LatticeMind, all you need to do is basically just plain language, and then you can get the results. So this is excellent for engineers or experimentalists working in a lab, and maybe they don't have access to a theorist. They could just go to LatticeMind and ask it a material science question, and then get the DFT result calculated for them. Is it possible to a certain degree that working with these things prompt to complete program? Oh, these domains, finite element analysis, computer-aided engineering. So that would be more in the ballpark of QTCAD. But your question is probably more like engineering in classical engineering. But we might be working on that soon also. So for LatticeMind is definitely we're definitely considering expanding LatticeMind's capabilities with new solvers and expanding into new domains. So it's not just limited to DFT. All right, this calculation is almost done. And I want to point out, this is 100K tokens, but it's on a mini model. So this entire calculation is like on the magnitude of $0.01. If you went to Gemini Pro with 100K tokens, it's probably going to be $0.1. It's a 10 times difference. $0.1 don't sound much, but if you have hundreds of calculations and hundreds of prompts, then the difference in the costs can become quite significant. So we have a new project complete. I'm going to interrupt this and start the new project right now so that we have enough time to complete the last problem. All right, new project. All right, K-point convergence study. So we're going to compare the energy of FCC aluminum using different settings for the K-point grid. So let's take a look at our previous result, gallium arsenide, and you'll see that I am confident we'll get a beautiful band structure. Yes, so we'll get a beautiful band structure for, and if you are in material engineering or material science, you'll recognize that we have several signatures that look exactly like what we would expect in gallium arsenide with the PBE functional. Please remember this is with the PBE functional, so the band gap closes. So, and if you want to open up the band gap, you would need to use an HSE functional. Might be possible, sir. Yes, okay, so that one is done. So you can see the new convergence study is being planned. All the input files are generated. The result files and the scripts. So these are, these are demo prompts because we have to do them very quickly. But you can think about how complicated this folder structure can get when you have real scientific projects, multi-stage projects. And you would want to make sure that your AI agent is being the most efficient when taking in the information and producing accurate results. The worst that can happen is it produces an input, then you submit to like Compute Canada or some HPC, it runs for 48 hours, and then you discover that the AI made a mistake. All right, so that is the type of stuff we're trying to prevent, and all the infrastructure is going to prevent those types of issues. That's why we spend so much time on benchmarking and evaluation and working with actual material scientists and studying their day-to-day workflow and incorporating their expertise and databases into LatticeMind. This is so nice on qBraid. Normally this on my laptop, this would take, maybe like more like 10 minutes, but this will probably finish in like 3 minutes. Nanoacademic looks really beneficial for extensive use of LLM and AI. Thank you very much, Maya. Thank you. So we're almost done here, and this will be basically my last live demo. And so we're on schedule, right, Alex? We have 10 more minutes. Yeah, for reserve for Q&A. Awesome, almost on the spot, on the dot.
Yeah, and we've been getting through a lot of Q&A too. So if you want to go a bit over,
Perfect.
We'll have time for questions still.
Yeah. All right. This is the convergence study. You'll see everything looks good. You get the energy curve. And you would see that. So if you're a material science test scientist, you'll see, okay, this is only a -8 MEV difference. So 10 by 10 by 10 is probably, pretty good for your future studies. So you can comfortably choose 10 by 10 by 10 for your studies in the future. So that is all from me for the live demo. So Alex so I'll stop sharing my screen. Oh, well, actually, one almost forgot. Please contact us here. So this is so for anybody who's interested in Nanoacademic or in LatticeMind, please contact us at either my email for LatticeMind related questions or for info@Nanoacademic for general inquiries, license questions, or anything. We're always happy to help. Awesome. So I guess we'll just look at the Q&A, Alex.
Yeah, great. Thanks so much, Nate. That was excellent. Definitely
Thank you.
a very in-depth showcase of all of the abilities of Nanoacademic. So I definitely got a lot out of that. Yeah, so we're gonna open it up for a Q&A here. We'll just take a second to read some of the questions that we have right now, and feel free to ask anything that maybe has been on your mind throughout the presentation. Questions about qBraid, questions about Nanoacademic. We're here to answer them. So we're just going to open up the floor and take a look at that.
Yeah. Oh, I see a question from Louis. Hi, Louis. Yes, transport calculations need structure checks, and that is we already have some checks integrated into LatticeMind as well. For example, for wires, for nanowires, but we're going to incorporate more sophisticated structure checks for larger structures. Absolutely, and that's what really differentiates LatticeMind from a generic AI agent orchestrator. We will have all of these physics consistency checks incorporated. Thank you, Louis. And we have, can we get recorded video? Yes, this video, I believe, will be uploaded to YouTube.
Yep.
Can't,
It will be on the qBraid YouTube channel, which I'll type in that question right now in the Q&A. So I'll send a follow-up email to everybody with the promo code, Nanoacademic resources, qBraid resources, and the video link. So feel free to go look at our YouTube channel there. We also have the NVIDIA webinar series as well and everything moving forward. So definitely take a look there.
awesome. You use the qBraid AI Gateway as Nanoacademic's open AI gateway. So I think, so these are two different assistants. One is for launching jobs and interacting with components or walking you through steps on qBraid. And LatticeMind is more for first principles calculations, orchestrating your workflows, and doing the calculation. So there are two different AI assistants.
Absolutely, yeah. And I think there are ways to integrate them together, right? We have
Absolutely.
qBraid MCP, which is now live, which you'll see announcements about coming up. So if you have other tools and you want to integrate both Nanoacademic and qBraid, say you want to submit some real quantum jobs, then you can start with LatticeMind, get your project there, and then maybe transfer over to qBraid Gateway so that you can actually run that on real quantum hardware.
That'd be awesome. And something that gets me very excited is different agents like working with each other. Um, we're going
Absolutely.
to have a whole army of different agents orchestrating and interacting, almost like a little agent society. So that's something that's very exciting.
Right,
Uh,
with different expertise, right? LatticeMind
yeah,
is very has a very certain expertise, and very broad,
yeah,
and qBraid as well. So
yeah.
also one of the examples somebody asked, if I'm not familiar with DFT, right, LatticeMind definitely allows you to just use plain language. But if you're brand new and you don't know anything, maybe you start with qBraid chat just to ideate and get some ideas of what is DFT in the first place and what
Yeah,
could I do with it, and then you launch an instance and you get started on LatticeMind.
yeah, absolutely. And I should mention that LatticeMind has an AI interface. So if you have like Codex or you're using the qBraid AI assistant or anything, you can let your AI agent interact with the LatticeMind AI agent as well. Can LatticeMind suggest follow-up collections to strengthen our hypothesis? Yes. Actually, let me see if it's in here. Usually, yes. So next steps. you can see that LatticeMind usually produces some next steps recommendations for you. So, and if I scroll back up into the band structure calculation, it will probably have some next step suggestions as well. Validations and checks, next steps if you want to extend this. The usual projected analysis or projected DOS, spin polarized tests only if there's magnetic perturbation, a denser K-point study for convergence check. So yes, LatticeMind can absolutely suggest next steps for your calculations. Is quantum espresso software included in this? So currently not yet, but we're, as mentioned, we are definitely looking to expand LatticeMind's software capabilities and coverage. What do you think? Limits LatticeMind vis-a-vis two things, multi-stage increasing. So I think so for LatticeMind, the focus is of course first principles calculations, which is our expertise. And there's a reason why you want your AI agents to specialize, because if you have your AI agent branch out to too many topics, there could be there's lots of studies in this. There would be performance regressions, because at the end of the day, we already have very good generalist AI models like OpenAI and Gemini and Claude. So what we need on top of that are very specialized AI agents that can actually get the job done for you. So we need both, right? And for expansion into other domains, then we would need to develop new specialized agents into those domains. Can we reproduce the results on the qBraid platform? Yes, absolutely. So if you follow the quick start tutorial on the Nanoacademic Explore page and install the latest version of LatticeMind, which is version 0.3.1. So please double check that it's 0.3.1. You will reproduce everything I've shown in this live seminar. If I have my own computer, want to run it locally, can this be applied to your site? Yes. So if you have your own Ollama model or own self-hosted model, yes, you can switch the provider in LatticeMind and use it with your own model.
Yeah, and also on the qBraid side, qBraid SDK can be installed locally. So on your local machine, regardless of what it is, you'll be able to have all of the features of qBraid directly from there, including like qBraid I Gateway, including job submission. So everything that you see on the qBraid platform, all of the tools that it provides you a visible access to, you could do on your own hardware as well through the SDK and qBraid CLI. Great. Yeah, I think, Nate, I'm gonna give some closing statements, just some final announcements. But that was
Perfect.
an amazing presentation. Thank you so much
Thank
for
you so
taking
much.
the time and walk through that. Yeah, you did a wonderful job.
Thank you.
So, yeah, of course. A few things to close. So we will be having one more, or sorry, two more qBraid community webinar series sessions. The next will be Rigetti, and that you'll see an email for that in the coming weeks. It will be on September 9th. And after that, we will have a to be announced session, which just keep an eye out for because we're excited about our final session there. If you have any questions, definitely email either Nanoacademic if it's Nanoacademic related or contact@qbraid.com and we'd be happy to answer your questions there. I'll just share quickly here to show you a couple things. First, if you missed that short demo on how to get your credits, all you're going to need to do is create a qBraid account by going to account.qbraid.com or just go to qbraid.com and click a get started. And from there, you'll be able to see this dashboard page. What you're going to do is go down to wallet and use that Q Community 50 on this buy credits section. Just click add credits and do Q Community 50, and you'll be able to select how many credits you want to purchase, and you'll be able to get 50% off there. So if you missed that, that is how you go through. Here's our qBraid YouTube channel. So if you happen to miss the second half of this lecture, a previous one, we have some videos here from previous sessions as well as our qBraid office hours. And also our documentation. People had questions about AI Gateway. Just go to docs.qbraid.com and I'll drop those links as well. Again, all of these resources will be in the follow-up email that I'll send after the presentation. One last thing is that we currently have our qBraid Quest program going on, which is quest.qbraid.com. If you are interested in academic side of quantum computing or using our platform for a research purpose or course, then please apply here. We'll be closing applications soon if you're interested in gaining free access to some of these resources on qBraid. Great. Yeah, I think that's all I had. Again, I'll send a follow-up email with these resources. And again, a huge thanks to Nanoacademic, especially Nate and Jeremy, for showing up and giving this great presentation today.
Thank you so much, Alex. It was a great pleasure.
Thank you, everyone. Thank you for joining, and see you soon.
Awesome. We'll end it there. Any questions, just send an email. Thank you again, everybody.
Thank you.
Bye.
Bye, everyone.
Bye-bye.